Hello, thank you for those of you who have survived this long into this wonderful conference. I thought everyone here would either be gone or asleep, but some people have soldiered on. I'm Eric Weisstein. I would like to talk to you today. I misspelled something, didn't I? That's not good. About a project that I've been involved with to encode mathematical knowledge of a more abstract nature in the entity property framework of Wolfram Alpha and the Wolfram language. And this is work done jointly with Cong, who will be giving the second part of the talk, and a couple other collaborators that I'll mention here in a moment. So as an introduction, the idea, we have lots of data collections in lots of areas. We have mountains, glaciers, people. But in terms of sort of real and more abstract mathematical objects, we hadn't really pushed our system very far to see what we could do. And those are things that we would really like to be able to encode and make computable. So Stephen Wolfram and Mike Altrott had this idea that an area of mathematics called function spaces would be an interesting testbed to try this out on. So a group of us, starting in December of 2014 and ending summer of this year, tried to do this. And this includes Chris Stover, who is a grad student at Florida State University and also works part-time for us, myself, James Molnix, who sitting up front and has been involved heavily in semantic math initiatives, and Lynn. So at the end of the day, this sort of consists of three new domains: function spaces, and then a more abstract version that we decided we need to split off, topological space types. This is still developmental in Wolfram Alpha, which means you can't see it on the website, but it is hooked up in the EntityValue framework. So if you happen to get a copy of this notebook and try it, some of it might work even outside the Wolfram network. So some challenges with this particular domain is that it requires a fair bit of math knowledge. And I'm a physicist, astronomer, data collector. I'm not a pure mathematician. So in order to do a project like this, you need people who know math. And luckily, we have Lynn and James and Chris to provide that expertise. As in a number of areas, literature is very scattered, so it can be difficult to go through, even for a human, to find out what somebody means when they refer to something. There are different conventions. And the entity framework of the Wolfram language wasn't really designed to have kind of entities that have pre-parameters floating in around in them supported. So those were some challenges. Just a little bit of background really quickly for those of you who aren't topologists or analysts. A function space it's a set of functions that basically goes from one set to another. And it's called a space because it has these properties. In many applications, it's something called a topological space, and it has various notions of measure. So common examples you may or may not have heard of. There's Lebesgue spaces of functions that sort of have natural generalizations of norms. And there's CK spaces, which have sort of continuity and existence properties for derivatives. So that's the first piece. Then there's a more abstract version of which function spaces kind of are particular instances, and that's a topological space. And that's a very general mathematical object in which these objects satisfy certain low-level axioms related to points and neighborhoods. And it appears even in places like physics and other places. So there's a lot of math that actually depends on these notions and terminologies. And the two most common examples, Hilbert space and Banach space. So what did we do? Well, at the end of the day, we collected 126 of these function spaces, almost 40 of the topological spaces, and then because it's important to cite which conventions and such we used, we, of course, collected all the resources and citations that we'd used. So here, let's see. Let's take a risk and actually evaluate. Oh, it worked. OK. So here in the function space domain is a set of 5 of the guys that we have. And you can do things like find out all the ones that are related to this notion of Lebesgue space. And since my colleagues have been doing this, I figure I'll just show you in all bloody, gory detail, too. There's the whole list if you really want to see them. There's a substantial amount of work involved in these compared to, say, curating mountains. As you can see, there are many free parameters, and Lynn will talk a little bit about some of the challenges that he had to go through. So here are some of the properties. or actually all of the properties that we attempted to curate for these. And here is what it will, more or less what it will look like on the Wolfram Alpha website once we get final design approval. So you type in the name of the space or some representation of it, you get its nice little definition. You can see there's actually annotation. So when we mark up the human readable definition, we semantically encode some of the notation. So we get these sort of annotations for free. We make a little graph, which we'll have more to say about. And then you get basic properties, what's its measure space, other notations. One particularly useful thing, at least that I have found, is the notational differences. This is a very common space, and there's already multiple different ways that people refer to it. So we can actually collect these together and show you who used what. Okay, norms, inner products, and so on. All right. And again, just to show you, so these are, what you see are these nicely formatted entity blobs. You've probably seen those at a couple other talks. If you look at the input form, this is what the thing looks like under the hood. It's just an entity in the domain function space, and it's got this slightly funky standard name that Stephen Wolfram doesn't like, but so may change before it actually gets released, but you can kind of see what it means. And we have parameters, eponymous people, related spaces, and again, just to kind of show you in all its gory detail, these is the complete set of properties that is curated for this space. Okay. So one of the unique things, I'm not sure that you can see well enough to see it, but if you can see it, you'll notice that in this entity standard name blob, there's some typeset notation, but inside that notation, there's actually some variables. Those are those funny little things with the dot above and below. That's a formal variable in Mathematica. So this is not just a fixed thing. This is, we can do a substitution. You know, we can just substitute in a particular value of p goes to 1/3, or p goes to 3, or p goes to infinity. And the properties of this space, this is what it would be for, in general, in the most general case, we can say that a Lebesgue space with parameter p is a member of these topological spaces. But you can say more about it for particular values. And you can see that the norm, for instance, is some piecewise function depending on the parameter. As you plug in different values, you actually have to be able to handle that. And you switch from, in the infinity case, from an integral like that to an essential supremum. Okay, so I've raced through that a little bit. I'm going to let Lynn take it from here, and hopefully we'll have plenty of time to show more examples or answer questions when we're both done. And sorry for any static in transferring the microphone.
Hello? Okay, so I'm going to talk about this topological spaces. So when we started this project, we put everything all together. So we put Hilbert space and Lebesgue space all together. And later on, we realized some of these spaces are more abstract than the others, or even though they are abstract spaces. So somehow we separate this project into two sub-ones. So the one Eric already introduced are called the function spaces. So like the Lebesgue space, there are some concrete ones. There are particular functions, a collection of particular functions with particular properties. And now I'm going to introduce some more abstract topological spaces. So most famous maybe this Hilbert space or the Banach space. And for them, we also have the properties, but you can see here they have less properties than the function spaces. That makes sense because they are more abstract. Let's see what it really looks, for example, for the Hilbert space. So like the function space, first you will have the name, you will have the description, and you have this relationship graph, which I will introduce shortly after. And here are the more general classifications. Means if you have a Hilbert space, you will know it's a Banach space, it's a Barrel space, such and such. And there are also some examples, like what function spaces like in this topological space. So for example, you can see this the big space is a special kind of this Hilbert space. And you have this formulator, you have the timeline, all the authors, and then you will have these references. And each of these are clickable. Let's go back. This is like this is all the properties in detail. So first, begin with the names and the example function spaces as shown on the website. So this is what our data really looks like. We didn't include the formulation date for this Hilbert space. This partially because Hilbert himself didn't really raise the name Hilbert space. It's like Hilbert mentioned some species has these wonderful properties, and one of his students just use it in his papers and called, well, in the spaces in Hilbert's paper, and later on people just called, well, in the space in Hilbert's paper or in Hilbert's space, later on just called Hilbert space. And one day when Hilbert himself went to a conference like this and he hears the audience and somebody just talking about Hilbert space, and he just asked one of the neighbors, okay, what's a Hilbert space? Okay, that's a joke. One thing really wonderful about these topological spaces is this relationship graph. We'll see here. So now I'll use the example for the Banach space. Banach space is one of the most studied topological space in functional analysis, in star algebra, in operator theories. So given a space which is a Banach space, we always know it belongs to this Bayer space, this Bayreuth space, this broad logical spaces, and is complete, is normed, it has a lot of other subsequential properties. So in other words, for these topological spaces, we can have this hierarchy structure. So you can see at the very top is a Hilbert space. And the Hilbert space itself is an inner product space and also a Banach space. And a Banach space will always be a norm space. And a norm space will always be a complete space. So in this way, we combine all these abstract spaces together. But this is not the full list of all the topological space in the world. These are only the ones we concerned within this project. And these are self-constant within this project. So it kind of, this graph is not super connected. If you can see here on the left, there are some spaces that belongs to this Polish space. And on the right, all these spaces lies in this topological vector space. Well, this is because by doing this, we have combined different notations by different authors from different references. So some of the authors just interested in these topological vector spaces, and some of the authors just interested in the locally convex spaces. But in general, some of the spaces are just a topological space with no further structure. So we combine them together, and we want them to consistent within this project. So for every topological space within our project, we have our own definition. Likely we will use the most acceptable definitions, like for the Banach space is just a complete normed space. And if you see like this, it's like this node and edge graph. So it really shows this hierarchy structure. Now, how are we going to use this? Like for example, for this Lebesgue space L2, we can see evaluate is relationship graph. I'll make it bigger. So like later on in the website, actually we already implemented this. So for this L2 space, we will know it's a Hilbert space. So everything that in red means this L2 space lies in, and everything in gray means it's not necessarily one of these space. And by our previous graph, we have a lot of this implication edges. How can we make sure that we are self-constrained within our project? So Eric made a lot of tests. It's called Eric's tests. So we just want to make sure we didn't make any error. So for example, this is just one of maybe hundreds of these tests to make sure everything in the previous graph is correct. So let's see. Whoops. Oh, it seems we missed someone. So this means we should have this borrowed space to get this Mickey space, but we didn't include them under this Browner space, Smith space, and stereotype space. This is not really a bug. It's like we want to show we can really check our correctness here. So that's why Eric manually deleted these two edges on the website for now. And one side product of this project is all the references we use. So roughly we have more than 100 papers and books for this project. We listed them all as entities on the website now. So it's quite standard for each reference. You have its own property. And we also made some classifications for these references. Like for example, you can find all the functional analysis papers written down by a particular author, or written down in particular language, or even during particular time. So let's see some examples. Maybe see this Bethel's 1959 functional analysis papers. So this will give us the paper that Bethel written in 1959 about this functional analysis. And if you click this paper, you can go to its own page. Now I'm going to introduce some examples from this product. So this product is more than a regular, more than an entity. It's really a computable entity. So for example, we can check something. We know there's a famous theorem that for any p greater than 1, the dual space of LP space is LQ, where 1 over p plus 1 over q is 1. So really, our entity table knows about this, so it knows how to compute its dual space. Okay, now let's try to compute the dual space of its dual space. So the dual space of LQ, or it is something looks much complicated, but we can do the simplification. And its LP space itself. And all these entities can be checked whether or not they are equal. So we check, yes, our answer, it is equal to this LP space. Now, there's another thing. If the bidual of a particular function space equals to itself is called a reflective space. Now, here we can see that the dual space of dual space is called bidual. The bidual space of Lebesgue P space is Lebesgue P space itself. And we can check this is true. So which means reflexive space should be one of the properties for this Lebesgue P space. Well, it's true. We really mentioned this LP space is a reflexive space. Next example. So for a particular function space, we have its inner product, if applicable, and we have its norm, we have its equivalence relationships. All of above, they are pure functions, and which means they are really computable. They are so like for the L2 space. We have now we define two functions f1 and f2. We can see we can check these f1 and f2 are the members of this L2 space. Now let's compute its norm. So notice actually in our this entity property table, this pure function itself is not really computable because we have our own Wolfram language extensions like this measure space, like this the big measure. Is not really computable for now, but we have this nice function from entity. We can, for now, make it computable. So if apply this from entity to this L2 norm, we will just have this regular L2 norm for the real line, and we use just the regular integral to represent this the big measure, the big integral. And we apply this L2 norm on those two functions, and we can compute them. So we have two crazy numbers, which means it's really computable. We can compute these two numbers. OK, for this L2 space, we know it's a Hilbert space. So it also has an inner product. And we apply this inner product on these two functions. It will give us an answer. And we know there's a famous Cauchy-Schwarz inequality, which states that the absolute value for the inner product is less or equal to the product of those two norms, those two L2 norms. So we can see here in our entity table, it really knows there's a Cauchy-Schwarz inequality for this the big 2 space. And we can check, and this absolute value for the inner product is really less than the product of those L2 norms. So it returns true. So it means things within our project is self-constant and is computable in some sense. The last example I want to show you is some new species called Campanato-Morrey species. These species are really new compared to these Hilbert species. They were only introduced like in the within 15 or 16 years. So there are not many papers or books really on this species, and their definitions are not super clear. So one challenge about this about this product is we need to compare all these notations, all these definitions within different references. You can see from here, different authors may use different parameters. Different authors may use different notations. And even though some authors may use the same parameter, those parameters may mean different things. So in our project, we just try to make our things self-constant and really connected with the other entities we have in our project. And also for this Morrey space, there's an alternative definition. So for this particular space, different authors has different different intentions on it. So for a particular same space, we have even two definitions. OK. Thank you, everyone. That's all. So any question?